Today we are going to finish up our little introduction to limits, and we're going to do that by looking at some of the limits that you can calculate quickly by hand. So here, there's some rules. The first one says, if a function is continuous at c, then the limit as x approaches c of f of x is equal to f of c. If we have a continuous function, something like this, and say c is here, if it's continuous, so continuous again means I don't have to lift up my pencil as I go past that point. And if it's continuous just at that point, then the limit as x approaches c of f of x. So we're looking at the number that the function approaches from the left and from the right as x gets closer to c. That limit will be equal to f of c. Remember, f of c is the y coordinate of this point, where the x coordinate is c. So this point is c comma f of c. So if it's continuous, you're going to go through that point, and the limit is equal to the y coordinate of that point. For example, if I want to find the limit as x approaches 2 of this polynomial, every polynomial function is continuous everywhere. So I know it's continuous as x approaches 2. So if I want to find the limit as x approaches 2 of this function, it's going to be equal to, so let's just call this function x, it's going to be equal to the function value at 2, which means I can calculate it by plugging 2 in for all the x's. And once I plug this in, I would then type that on my calculator, and I would get an answer that the limit as x approaches 2 of this function f of x is 41. If we graph the function, the point 2 comma 41 would be on the graph, and the graph would be continuous through that point. So if it's continuous, you can plug in the c value to get the limit. What happens when it's not continuous at c? So here I have the function r of x equals x minus 2 over x squared minus 6x plus 8. Let's factor this denominator. This is x minus 2 and x minus 4. So this function is undefined at 2 and at 4. Now, there's two different things happening at those points, because we see that these x minus 2's will cancel, and the function simplifies to the function 1 over x minus 4, but still undefined at 2 and 4. Depending on what the behavior is, we'll have something different happen at the limit. We look, the x minus 2's cancel. So if we want to find the limit as x approaches 2, what we know is there is a hole at x equals 2. That means that this graph looks exactly like 1 over x minus 4, except with that single point removed. So if I want to figure out what the limit is, that's the value that the graph approaches on both sides of 2. It'll be the same value that it hits in the simplified form. So what you can do when there is a hole is you substitute the c value 2 into the simplified form of r of x. So I can take the 2 and plug it into this function, and I get that the limit as x approaches 2 of r of x is 1 over negative 2, or negative 1/2. Now there's something different happening around x equals 4 on this function, because that does not cancel out. What we know is that there's a vertical asymptote at 4. Now, there are two different things that can happen at a vertical asymptote. At a vertical asymptote, the graph can either go up on both sides, or it can go to positive infinity on one side and negative infinity on the other side, like so. And we actually had a rule when we did rational functions to tell us which way it happened. And that was to look at the exponent in that factor. This is an x minus 4 where it's the first degree. So we know that in this case, the graph is going to go to positive infinity on one side of the asymptote and negative infinity on the other side. But you may want to take out your graphing calculator and look at the graph to check the behavior around the asymptote. Because one of these situations has a limit and the other does not. If the graph goes to positive infinity on both sides, then the limit would be positive infinity. But in this case, where the graph is going to positive infinity on one side and negative infinity on the other, which is the case for r of x, we would say that the limit as x approaches 4 of r of x does not exist. Excuse me. So the last part of this is just a little preview of why limits are important in calculus, and there's many places that they would show up. But this is one case. This says find the limit as x approaches 2 of the average rate of change of this function f of x. So average rate of change is the slope. So we want to find the limit as x approaches 2 of the slope, the change in y over change in x for this function. And we want to do it from 2 to x. And this is something we did earlier in the year. The limit as x approaches 2 of f of x minus f of 2 all over x minus 2. This is change in y over change in x. And then we would find the value of f of 2. 4 plus 6 is 10. So this is the point 2, 10 on the graph. And I'm going to plug that in. I want to find the limit as x approaches 2 of the function minus the function value at 2, which is 10, over x minus 2. And if we factor this numerator, it's x plus 5 times x minus 2. So the rule on the previous page said if you wanted to find the limit as x approaches a value and it's undefined at that c, you can simplify and then use the simplified form to plug into. So I'm going to find the limit as x approaches 2 of this simplified function, which is equal to what I get when I plug 2 into that simplified function. Now, what does this all mean? What have I calculated? Average rate of change is the slope of a curve between 2 points. So this graph is a parabola, and I'll show you the graph on the other page. If you're doing average rate of change, you're finding the slope between 2 points, and you can write the equation of a secant line. This is poorly drawn. A secant line goes through the graph at 2 places. Here, because we found the limit as x approaches 2, what we're doing is we're finding this average rate of change, the slope between 2 points that are closer and closer to each other until you get the limit as x approaches 2, which is the slope at a single point. So what we actually found here, and this is where calculus goes, and this becomes the derivative. What we found here is the slope of the tangent line, which hits the graph at a single point. So here's x equals 2, and the graph, x squared plus 3x. And then what we found was that the slope was 7, the slope of the tangent line. That was the limit. If I use the slope of 7 and the point 210, what I get is this equation of a line, y equals 7x minus 4. And when I graph that, I see it touches the curve at a single point. In calculus, you use the derivative to find the slope of a curve at a single point, and the derivative comes from this whole discussion of limits. So that's where this is going in calculus, and unfortunately we don't have any more time to kind of give you a little more preview of that, but there is a real application and reason for these things that you will see if you take calculus next year or any time in the future. These are the last notes of the year. So there's one more assignment and then a little graded assignment tomorrow. I want everybody to join the meet at the start of class tomorrow. That is the seniors' last day. See you all tomorrow.